Have you ever taken a look at a piece of plywood and thought, there's just too much wood in that? Does every layer really need to be wood? To be honest, I've never thought that either, but that didn't stop me from removing one of those wood layers, cramming in some electronics, and making this. This is a headphone stand that I made by bending and laminating thin layers of wood around a clear plastic light guide. The light guide is stuffed with addressable LEDs and capacitive sensors to detect touch. Figuring out the process to build this has been a huge undertaking, so today I'm going to walk you through what it's taken to make this. Let's get into it. Like all good projects, I started planning this one many years ago. I saw a post online of laminated shelves that curved around corners, and I decided to do something similar. So I saved that webpage into my archive, and by that I mean I left a tab open on my phone for at least 3 years. Then, around 6 months ago, while working on my tile backsplash project, I got re-inspired. So here's the idea. We're probably all familiar with plywood, which is made up of thin layers of wood glued together with alternating grain directions. This results in a rigid panel far stronger than the individual plies. There's another advantage to this approach though. Thin layers of wood are bendable, so building non-planar wood structures is relatively simple. This is actually a common technique in woodworking called bent lamination. While mulling over this project, I had another thought. I'm not restricted to wood when making these laminations. Anything that can be appropriately bent and adhered can be used as one of the layers. And that got me thinking. If I embed clear plastic as a layer, I can use it as a light pipe. Individually controlled LEDs inside the wood could shine through this layer, lighting up the edge of the wood. And how cool would that be? RGB lighting that runs up and down the edge of a functional piece of wood. Now, I'm not one to take on too small of a project, so I pondered other things to add to the lamination. In my tile lights project, I used microphones to detect touch with mediocre results. But many comments asked why I didn't use capacitive touch sensing. Part of the reason was that I didn't have any experience with it, so I decided to dip my toes into the water by adding it to this project. So here's what I want to build. I'm going to make a 5-layer lamination with the outer layers being wood with alternating grain. The middle layer will be clear plastic with flexible circuit boards that run along the midline. These circuit boards will contain addressable LEDs, a microcontroller, and a pad where a larger capacitive touch sensor can be connected. The touch pad itself will be cut from copper tape. I will bend the wood over 3D printed forms, lather it in adhesive, stack it together, and throw it in a vacuum bag over the mold to clamp it all together. I've got a few different ideas of what I want to make with this technique, but I'm going to start small to prove the process. So today, I'm making a simple headphone stand. This is a good first build because it is a reasonable size, but it still has 3 1-inch radius bends, which is representative of what I want to use in future projects. One of the first tasks is material selection. I need thin layers of wood to make up the laminate with the requirements that it be bendable and aesthetically pleasing, at least on the outer layer. Wood veneer seems like a great option, but there are a couple issues. First, veneer is almost always backed with either a thin layer of low-grade wood or with paper. This would be visible on the edge and could lead to bending issues, so I really wanted pure wood. Second, veneer tends to be very thin, like a 1/40 of an inch. So to build a 1/4 inch thick structure, I would need something like 10 layers, which would add a ton of work of bending and gluing all those layers. But I stumbled upon a great solution. 1/16 inch thick maple. Maple isn't the most exotic wood, but the grain is pleasing and it's very common, so there's lots of info on working with it. And it's easy to find thin plies because it's used to build skateboards and snowboards, which is really similar to what I'm doing here. So I bought a big pack from a company called Roar Rocket, no affiliation, which specializes in board building. These all have the grain in the long direction, so I also purchased a considerable amount from eBay in the form of skateboard building kits, which also contained cross-grain plies. With the wood on hand, I needed the light guide and the electronics. I wanted the light guide to be flexible and roughly the same thickness as the wood. After some searching, I ordered PET plastic, which met those requirements. More on that later. As far as electronics, I'm going to use the SK6805 addressable LEDs that I used in my tile lights project, except in a different package. I want to mount the circuit boards parallel to the light guide, so I need the LEDs to shine sideways in this application. I settled on this tiny package that's less than 1 millimeter tall. I whipped up a flexible board in KiCad, which is very small and simple. It has the option for up to 4 LEDs, but the LEDs are bypassable with a resistor, allowing me to only install the ones that I need. There's a cheap PY32 microcontroller to handle touch sensing and serial communication. And lastly, there's this tail that connects between boards. I made it this shape, hoping to improve the in-plane flexibility in case adjacent boards don't exactly align. These boards are sized such that there's one every 1 inch along the assembly. Going into this, I knew there would be 2 challenges. First, getting the materials to bend with a 1-inch radius. This is tighter than you usually see this technique used for, and there's probably a good reason for that. The second challenge is gluing to the plastic. Most plastics have low surface energy, which makes bonding to them tricky. I also need a long working time to assemble the parts, and I want an affordable, light-colored adhesive. Before spending time and material bending bigger prototypes, I decided to do a few flat ones to test the glue-up, vacuum bagging, and electronics. First was this very simple lamination with just a copper pad in it, only to test the capacitive touch. This allowed me to verify that the PY32 would be sufficient to act as a capacitive touch sensor, since it doesn't have a dedicated peripheral built in. In just a few minutes though, I had the software working well enough to give me confidence. Next, I built a flat prototype 5.5 inches square with 5 circuit boards and touch sensors. Although the geometry is simple, this is fully representative with the clear light guide, circuit boards, and LEDs. The boards are daisy-chained, so the final design will only have 1 wire connected at the end, but being a prototype, I connected to the programming ports of each board, just in case I need to tweak the sensor code after assembly. Making the capacitive pads was simple. I cut these to 5¼ by 0.9 inches from copper tape using my fiber laser, but this could easily be done by hand. After the first prototype, I added holes for adhesive to pass through, otherwise I'd just be relying on the tape's adhesive. I epoxied the circuit boards to the light guide, threw the touch pads on and soldered them in place, laminated the layers, and put them into a vacuum bag with a 3D printed mold. And it was a disaster. But oh boy did I learn a lot from this first prototype. First, PET doesn't laser cut particularly well on a CO2 laser. I got through it fine, but it's definitely not acrylic. Second, my capacitive touch software approach was total garbage. It was way too sensitive to noise and variations in wood thickness. More on that later. The biggest problem, by far though, was adhering the layers together. To prep for bonding, I left the wood layers untouched, and I sanded and flame treated the surface of the PET. This is a neat trick where you run a gas torch over the plastic, which chemically modifies the surface, improving the surface energy. To show you how well this works, I did a water break test. The left is not flame treated, and the right is, and the result is pretty obvious. Water rolls off the left side, but it spreads out and wets large areas on the right. After treating the surface and gluing the circuit boards in, I masked them off and gave each side of the light guide a coat of white primer. If you've dealt with optics before, you're probably familiar with total internal reflection. Light that strikes the surface below a certain critical angle, which you can calculate from the refractive indexes of the materials, will reflect and stay within the light guide. LEDs are not collimated light sources though, so some light is going to leave off-center, and you can usually figure out how much from a plot in the datasheet. This white paint will act as a reflector, helping to bounce light rays back in should they escape. As far as adhesive, I did some research and found a few sources recommending Cascamite for laminations, so I decided to give it a go. This is a wood glue that comes as a powder and gets mixed with water to activate it. I decided to try it not just between the wood layers, but also between the wood and plastic. So I mixed and applied it roughly per the instructions. Once it cured, I trimmed the edges with a router and wired it up to test it out. The results were disappointing, to say the least. The LEDs worked, but they weren't as bright as desired. The touch sensors were inconsistent, and 2 of them didn't work at all. And the glue just didn't stick. The prototype started to delaminate by itself, just sitting on the bench overnight. Even the wood-to-wood joints started separating. I quickly cut my losses on the first prototype and moved on to the second, changing a few things. First, I switched to this Total Boats structural epoxy for the adhesive. Second, I conformal coated the backside of the circuit boards just in case something was contacting and throwing the touchpad off. And third, I got rid of the white paint, since it didn't stick particularly well to the plastic. I again used a vacuum bag, and I cured the assembly on this silicone pad warmer set to 60 degrees Celsius with a towel on top to keep the heat in. This turned out to be a little too warm though, as I softened and deflated the 3D printed mold, which was just made from PLA. After cleaning up the second prototype and plugging it in, I was again disappointed. The touch sensors were acting up, and the epoxy still didn't bond sufficiently, although it was much better. But now the LEDs weren't shining through. And this was weird. I could vaguely see a couple of them working, but the majority of the 12 LEDs seemed to not work at all. Some troubleshooting showed that the LEDs were still turning on, I just couldn't see them. As a test, I threw a piece of PET plastic on the heating pad in the same manner as before, and to my surprise, I found that it actually got to around 90 C despite being set to 60. This turned the plastic opaque white, totally blocking the light. At this point, I gave up with the PET and went with what I know, which is clear acrylic. This laser cuts beautifully and it can handle the heat, but it is rigid. One thing that's been working great on this project are these circuit boards. And that's because I got these flexible boards from the sponsor of this video, JLC PCB. JLC PCB provides excellent quality circuit boards at affordable prices, which allows me to do projects like this where I need hundreds of boards. Besides flexible PCBs, they offer conventional boards from 2 to 32 layers and a variety of substrates such as aluminum and Teflon. You're not locked into specific PCB features like with other manufacturers. You can choose your trace and via sizes, board thickness, solder mask color, pad finish, copper weight, and on and on. They are even running a special on their premium 6-layer boards, which come standard with great features like via in-pad, gold finish, and controlled impedance. And if soldering isn't your strong suit, JLC PCB offers PCB assembly with a huge library of components in stock. So if your next project involves ordering and building custom circuit boards, be sure to check out JLC PCB. You won't be disappointed. Be sure to use the link down in the description for $70 of new customer coupons. While waiting for the acrylic to arrive, I used the prototypes to improve the touch sensing code. Here's how this works. The touchpad is connected to 2 GPIO lines on the PY32. One pin is used to charge and discharge the pad through a 2 million ohm resistor, and the other connects to the microcontroller's comparator, and it compares the analog voltage on the touchpad to an internal reference. To determine capacitance, the touchpad is first pulled to ground to discharge it. The GPIO line is then switched to VDD, which slowly charges the pad through the large resistor. A timer is started when the GPIO switches and the comparator is activated. When the pad voltage rises above that reference voltage, the comparator triggers an interrupt routine, which records the timer value and it returns the touchpad back to ground. All of this takes on the order of hundreds of microseconds, and it repeats over and over again. The speed at which the capacitor charges depends upon its capacitance, with a bigger capacitor storing more charge and taking longer to charge. Detecting touch works like this. The sensor has some base capacitance, and when you touch it, you add additional capacitance in parallel. Capacitors, of course, add in parallel, so this increases the overall capacitance, making it take longer to charge. The timer and comparator are used to record this charging time and determine if the sensor is touched or not. Now, calculating the base capacitance and the change when you touch it would be absurdly complicated, as it depends on a wide variety of environmental factors. So instead, I'm just looking for a sudden increase in timer value, regardless of what the actual value is. As with most things, this is conceptually simple, but the devil is in the details. The capacitance we're talking about here is on the order of picofarads, and the change in capacitance when touched is a fraction of that. With such low signal levels, noise is a huge concern. I implemented substantial averaging, but this still wasn't enough to guarantee stability. I researched this, and I found some great guides from Microchip, one of which recommended implementing a slew rate limiting filter. Basically, you keep track of the capacitance value, and every time you take a new reading, you either increase or decrease that saved value by a fixed amount, regardless of the magnitude of the reading. So if you get a bigger reading than your saved value, you add that fixed amount. And if it's smaller, you subtract that fixed amount. This means that outlier readings, which are way large or way small, have negligible effect on the stored value. In my case, I'm incrementing or decrementing the capacitance value by 1 every time. For reference, I have my touch threshold set to around 100 counts, so when you touch it, it takes about 100 samples to register as a touch, but that happens in a fraction of a second. The final issue I had to deal with is baseline shift. Over time, the non-touched baseline value of the sensor will shift in response to environmental changes like temperature or the proximity to other objects. To counteract this, I average a large number of samples and I recalculate the baseline every few seconds. With the software sorted, I got back to building prototypes. Since the layer adhesion on both prototypes was quite poor, I set out to find a suitable adhesive for bonding to the plastic. I did some non-scientific testing. I just glued a small scrap of wood to a scrap of plastic that had been suitably prepped. I cured it and I pulled it off by hand. The bond strength measurement was purely subjective. I tried a lot of different adhesives. BSI 30-minute epoxy, EPC 410, tabletop epoxy, total bud epoxy, they all popped right off. I had some black JB Weld plastic bonder left over from my tile lights project, and this bonded extremely well. So well the wood failed before the glue. But I can't use this because it cures in 5 minutes, which is way too fast to get the assembly together. What I settled on is this Westbond G-Flex. It's not as strong as the JB Weld, but it sticks okay, and it has an hour or so working time. It is easy to get, it's reasonably cheap, but it has to be the worst smelling epoxy I've ever used. And I've used a long list of epoxies. With the epoxy selected, I made a third flat prototype, this time with an acrylic light guide. This one turned out great. All the LEDs and touch sensors work, and the epoxy is holding strong to date. Bolstered by the success of the prototype, I set out making the headphone stand, which first required forming the wood and light guide. Even though the maple is just 1/16 of an inch thick, getting it to bend reliably has taken a huge amount of trial and error. These are just a few of the attempts that have failed. I had wood crack in half and split along the grain, numerous attempts that didn't hold their shape, and one where the grain delaminated right in the bend, preventing the layers from stacking. I tried many techniques, but what I settled on is this. First, I built a steam box from some scraps of OSB subfloor. I live at around 7,000 feet in elevation, so water boils at less than 200 degrees Fahrenheit here. And this is a real problem because it takes both water and heat to bend wood. I had to insulate my box fairly well, and I have to run it for much longer than recommended to get it hot enough. I'm using a 3D printed mold to bend the layers, and I printed clamping blocks for each of the bends as well. Only the 2 outer layers, the ones with the grain running along their length, need to be precisely formed, as they really do not want to bend without steam. For the outermost layer, I printed a sleeve that goes over the mold to get it to the perfect size. To bend a piece, I first close the box and start the steamer. While it preheats, I soak the wood in a tub of plain tap water. I searched for quite a while for a long enough container to do this in, before realizing that I have the perfect basin, as long as my significant other doesn't catch me. Now, wood likes to float, so I had to hold it underwater with the obvious tool for the job, a bottle of bubble bath and another bottle of horse, cow, llama, sheep, goat, dog, cat shampoo. After about 10 minutes, the steamer is steamy, I pull the wood from the bath and I pop it in the steam box. An hour and a half later, I remove it, carefully as I did get quite scalded removing one of these, and then I force it over the form with clamps. I then place it in front of a fan to help it dry. Wood expands considerably, especially in the cross-grain direction when it's soaked in water. The cross-grain ply of this expands by over an inch in length. It shrinks when it dries out though, so to prevent this from splitting the wood, I have to release and reclamp it after about an hour. I then let it dry overnight, and that's it. A reasonably well-formed piece of wood. I'd originally hoped that the light guide layer would be flexible enough to just form to shape, but it was immediately obvious that the 1/16 inch plastic just wasn't going to bend with a 1-inch radius. And the acrylic, well, it doesn't bend at all. I ended up preheating the acrylic to 120 Celsius in my reflow oven, and then quickly forming it over the mold using yet another spacer. On the topic of 3D printed molds and spacers, those also took a fair bit of experimentation. I won't get into it, but you're looking at least 100 hours of printing here. Once the parts were roughly bent, I tightened up the bends a bit with a heat gun, then I epoxied the circuit boards in place and used a reflow pen to solder the boards to one another, which worked great. With the wood and plastic formed, I decided to do a dry fit up, which wasted some bagging materials, but I hoped it would save the wood and plastic that I'd worked so hard to bend. There were a couple things I wanted to verify. First, the mold is 3D printed, and FDM printing isn't known to be watertight, so I wasn't sure if it'd hold vacuum. Second, I wanted to make sure that I could seal the bagging film, since I had to fold the bagging film over the edges of the part. It turns out that neither of these were huge issues. The mold held vacuum reasonably well, getting to around minus 25 inches of mercury, and sealing the bag took a bit of massaging, but it did work. Lastly, I decided to paint the insides of the inner wood layers white to help reflect light. I figured that the paint would stick well to the wood and the epoxy to the paint, making this a far better solution than painting the plastic. It took a tremendous amount of time to get to this point, but everything was ready to assemble. I decided to put the wood back into the steamer to soften it, and while it steamed, I mixed an entire cup of G-Flex epoxy. I had hoped that re-steaming the wood would make it conform to the mold better, but this turned out to be a huge mistake. All it really accomplished was allowing the wood to relax and lose its shape, which made it no longer fit the plastic layer or the mold. Having already mixed the epoxy, and being a little desperate to get this finished, I pushed forward anyway. I applied the epoxy and forced the parts over the mold with clamps. I installed the vacuum bag, turned the pump on, and nothing. I could not get this bag to seal, and now the misformed wood was fighting my attempts to fix it. To make matters worse, the epoxy was setting. But I kept trying, throwing more and more sealant tape, until finally, nearly an hour after mixing the epoxy, I started to pull a vacuum. I eventually reached an acceptable vacuum, but it took so long that I feared that the epoxy had already set up and my work was ruined. I let it finish curing under vacuum overnight, hoping for the best. The next day, I removed it from the bag, and I was pleasantly surprised. It is far from perfect, with gaps at the bends, but the shape is pretty close. It was much better than I was expecting, given how poorly the bagging went. I cleaned up the edges with a router and a sander. As far as gaps, I did what any subpar YouTube woodworker would do when faced with flaws in wood, and I filled them with epoxy. This took a fair amount, but after 3 or 4 syringes, I had them filled in. A quick sanding, and it was ready for finish. Maple can be tricky to stain, so I decided to dye these with trans tint. I wiped the color on, coffee brown, and let that dry, then gave it a very light sanding. Finally, I brushed on some water-based polyurethane. And here's the results. I'm really not happy with this finish, to be honest. I don't care for the color or the sheen, although at least the color is relatively consistent. Now for the moment of truth. Testing the electronics. I soldered the wires, hooked it up to an STM32 Nucleo, and it still works. The touch sensor thresholds are a bit high. I'll adjust those on the controller. I'm also going to 3D print a stand for this and code up some different animations. For the stand, I 3D scanned the bottom of this, which isn't the flattest, and dropped it into CAD. I then modeled a stand that mounts to the bottom and holds the controller. I switched to a smaller STM32 Nucleo 32, which fits in here nicely, with the USB cable coming out of the back. Some double-sided tape, and we're done. Usually this is the part of the video where I tell you how pleased I am with how this project has turned out. But, well, there's a lot of room for improvement on this one. No part of this turned out perfect, but the point of this was always to be a pathfinder. And man, I've learned a lot from building this. Bending wood, vacuum laminating, capacitive touch sensing. These were all things that I had never tried before. I have a number of improvements planned for the next iteration of this. One thing I'd like to do is to try to 3D print the light guide, which is deceptively tricky, but I'll get into that in a future video. I've redesigned the mold to make bagging much simpler. I also think I'm going to go to a slightly larger radius, even just a ½ inch bigger, which would make this process so much easier. Finally, I've learned some things not to do next time, like steaming the wood right before it goes into assembly. I'm also not going to spill the beans on what the next few projects I have planned for this are, so be sure to subscribe to keep up with my progress. That's all I've got today. Feel free to leave your thoughts in the comments below, and as always, thanks for watching.